Hi everyone, my name is Ben, and welcome to my tutorial on QUIC for SIT223 and SIT202. QUIC, or Quick UDP Internet Connections, is a transport protocol that's currently revolutionizing how we browse, stream, and connect online. In an era where speed and reliable are especially important, think like instant video calls or seamless mobile browsing, QUIC is becoming the go-to solution, with adoption growing rapidly. I think over 8% of websites used it by 2025. Today, I'll cover what QUIC is, why it's needed, its key features, advantages, applications, security, and scalability. I'll also dive into a Wireshark analysis to show QUIC in action. By the end, you'll understand why QUIC powers apps like YouTube and Google. And let's get started. First things first, what is QUIC? QUIC is a transport protocol built on UDP. It's combining speed, security, and reliability. It started as Google's experimental project in 2012 to speed up the web and was standardized by the IETF in 2021 via RFC 9000. Now it's the backbone of HTTP3, used by major platforms. Unlike TCP, which separates transport and security layers, QUIC integrates TLS 1.3 for encryption, making it faster and more secure. Now for why we need QUIC. Traditional TCP plus TLS takes 2 to 3 round-trip times, or RTTs, to set up a connection, which delays data transfer, especially on mobile or unreliable networks, like when you're streaming a video on a spotty 4G signal. QUIC cuts this down to 1 RTT or even 0 RTT for repeat connections, speeding up apps like web browsing or streaming. For example, loading a YouTube video on your phone is much faster with QUIC because it handles network hiccups better. It also avoids what's called head-of-line blocking, where one slow packet slows everything down, and supports connection migration, so your session doesn't drop when you're switching from Wi-Fi to cellular. QUIC is built for today's fast and real-time internet. For my visual learners, here is a visual to compare. On the top, TCP plus TLS needs multiple exchanges. First a TCP handshake and then a TLS, and then TLS, taking 2 to 3 RTTs before data flows. On the bottom, QUIC integrates TLS 1.3 into its handshake, so that encryption and connection setup happen together, often in 1 RTT or instantly for repeat visits. And that's QUIC's speed edge, making it ideal for modern apps. We'll dive into QUIC's core features now. It supports stream multiplexing, allowing multiple data streams, like video and audio in a Zoom call, for example, to travel independently in one connection, each with its own flow control. It's like separate lanes on a highway, preventing traffic jams. QUIC ensures reliability with packet loss detection and uses TLS 1.3 for security, as I've said, and supports connection migrations with what's called unique connection IDs, so your session persists during network switches. It also uses advanced congestion control, like the BBR algorithm, which adapts the network conditions better than TCP's older methods, optimizing throughput plus QUIC's loss recovery, like forwarding error connection, which helps with spotty networks. Now, let me get my laser pointer. Okay, now we're going to break down QUIC's packet structure. QUIC packets have headers, long headers for initial handshakes and short for data transfers, and they carry frames. That's down here. Key frames include the acknowledgement for confirming packets, and crypto for TLS handshake data, and stream for application data like web content. Each stream frame has a stream ID and offset to manage data order. There are also frames like ping to test connectivity and new token for faster reconnections. Most of the data is completely encrypted, except for minimal fields like the connection ID, which ensures robust security. All of this I will go into more detail in the Wireshark analysis. Now let's compare QUIC to TCP and UDP. QUIC's advantages include low latency with 0 to 1 RTT handshakes, no head-of-line blocking thanks to multiplexing, with strong security with TLS 1.3, which encrypts even packet headers. For example, when loading a complex web web page with images and videos, Quick streams ensure one slow image doesn't stall the rest, like TCP. Quick also supports mobility, so your connection stays alive when switching networks, like Wi-Fi to 5G during a video call, ensuring compared to TCP, which is reliable but slow due to multiple RTTs and blocking issues, Quick is faster and more resilient. Compared to UDP, which is fast but unreliable and insecure, Quick adds reliability and encryption. However, it does have its drawbacks. It was, after all, built by humans. Some firewalls block UDP ports, like 443, forcing it to fall back to TCP. Remember, Quick is built on UDP, so when it forces it over to TCP, it slows things down. Its user space implementation uses more CPU than TCP's kernel-based approach, and debugging is trickier due to encryption. Network admins often struggle to inspect Quick traffic with tools like Wireshark, but still, evidently, Quick's benefits make it a game changer for modern networks. The benefits far outweigh the disadvantages here. Onto network application and scalability. Quick powers a wide range of applications. It's the foundation of HTTP3, used by Google, YouTube, and Facebook for faster web browsing. Streaming platforms like Netflix rely on it to reduce buffering, ensuring smooth playback, and DNS over Quick. Secures DNS queries. SMB over Quick enables fast file sharing in Windows Server. And even for gaming, Quick is also a gaming traction in like some multiplayer platforms and IoT devices where low latency connections are critical for real-time data. As of 2025, as I said earlier, about 8% of websites use Quick, with browsers like Chrome enabling it by default, but this is going to skyrocket as you can tell so far. Quick scales impressively on massive traffic. That's this next slide here. Its multiplexing reduces connection overhead, and its user space design allows custom congestion controls like BBR, handling billions of daily connections on platforms like Google and Cloudflare. However, UDP throttling in some networks can limit its scalability short term, though adoption is really growing. Next, I'll jump into Wireshark now. Okay, let's get started. We're going to use Wireshark to analyze how Quick behaves in real traffic. I captured this HTTP3 session to bing.com, which again uses Quick for faster, secure connections. We'll examine two key packets to highlight Quick's handshake, encryption, and differences from TCP or UDP. Starting with frame 251, this is an initial Quick packet sent from my client to the server. You can see it's on port 443. Notice it's encapsulated in UDP, like TCP's direct use. Quick runs over UDP for easier deployment, but adds its own reliability. The UDP length is 1258 bytes, with the Quick payload of 1250 bytes. Here's the Quick header. The long headers are used for setup, including version and destination connection ID, which uniquely identifies the connection and enables migration. No source connection ID or token is here, which is typical for the client's initial packet, and the packet type is initial 0, marking the start of the connection. Inside, there are three crypto frames. The first at offset 81 with 754 bytes, the second at 835 with 23 bytes, and the third at 858 with 890 bytes. These carry TLS 1.3 handshake data. We'll look at the TLS client hello. It includes random value, the random value, cipher suits, and extensions such as the key share and supported versions. This all integrates security right into the transport layer, completing the handshake in just one RTT, which is much faster than TCP's separate SYN/ACK plus TLS, which is 2 to 3 RTTs. And there's also padding frames to align sizes and obscure traffic patterns for privacy. And see these three ping frames? They're QUIC-specific probes to test connectivity and elicit ACKs, helping measure RTTs without data, unlike TCP, which might use empty packets but lacks the built-in mechanism. Now let's look at frame 258, the server's response initial packet. It's smaller, 82 bytes total, from the server's IP back to my client on port 57876. Again, UDP encapsulation with quick payload of 40 bytes. It's a long header confirmed and initial 0, and we can see the source connection ID from the server. There's no destination ID or token as it's responding. The packet number is 1 and the payload is visible before encryption kicks in, partially visible before encryption kicks in. The key frame here is ACK. It acknowledges the largest packet number 1 with range of 0, which is meaning packet 0 to 1, and an ACK delay of 0. So QUIC uses these for quick loss detection and congestion control, which is more granular than TCP's cumulative ACKs. This helps QUIC recover from loss faster, especially on lossy networks. The source connection ID ensures session continuity during IP changes, which is a big edge over TCP, which ties sessions to IP/port tuples and often fails on mobility. Finally, most of the payload is encrypted, hiding details in TCP's visible sequence numbers or flags. QUIC's encryption, which is via TLS, prioritizes security and privacy, making it harder for middle boxes to interfere, but also trickier to debug. Overall, though, these packets show QUIC's efficient, secure setup, integrated TLS, multiplexing potential, and features like connection IDs that outshine TCP and UDP. In conclusion, QUIC represents a significant evolution in transport protocols. It's faster than TCP with its 0 to 1 RTT handshakes and multiplexing, more reliable and secure than UDP thanks to built-in TLS and loss recovery, and highly scalable for billions of connections in apps like HTTP3 on YouTube or Netflix. We've seen its functionalities, advantages, real-world uses, and even a deep dive into its packet structure via Wireshark, highlighting encrypted frames and QUIC-specific elements like crypto and acknowledgements. Of course, if you're interested, I actually highly recommend enabling QUIC in your browser settings just to see the difference in Google. But otherwise, thank you for watching. I hope this tutorial sparked an interest, and feel free to reach out with any questions.